Okay, hello everyone. My name is Nicole Park. I'm one of the course directors here for Data 8, and today I'll be guest lecturing on sample means. Joey's out of town. Typically, he does this lecture, but because he is out of town, I'll be lecturing today. And then make sure to come to Friday's lecture if you're in town as well, because Will Furtado, who's the other course director, will be lecturing on Friday. So let's get into this lecture. Some announcements to begin with. Homework 8 is going to be due tonight at 11 p.m. Make sure you get that in, and Lab 8 is going to be due Friday at 11 p.m. In addition, Project 2 will come out on Friday, but it's not going to have its checkpoint until the Friday after spring break. So you have spring break, and then you have a whole week to do the checkpoint. So unless you have like a really heavy midterm week, there's no expectation that you're actually going to get started on that project. If you want to get a head start, feel free, but we're just releasing it ahead of time in case there are students that do want to get a head start on that project. Any questions on announcements or anything before we get started? Okay, let's get into it. Some weekly goals. So this is just an overview of what lecture covered this week. First of all, on Monday, we covered the bell-shaped curve and its relation to random samples or large random samples. We'll be going a little bit more in depth to that today. Today, we'll be covering the central limit theorem. If you've taken any stats class, you've probably heard about this before. We don't go too into depth about like the conceptual parts about the central limit theorem, but you do have to understand how it works for this class. And then we're also going to cover the variability in this random sample averages. On Friday, you'll be going over designing experiments. So choosing the size of a random sample and kind of what that does to a experiment that you create. So let's get started with the central limit theorem. So sample averages are something that we are going to cover today. The central limit theorem describes how the normal distribution or a bell-shaped curve is connected to random sample averages. So the central limit theorem basically helps us to understand how a bell-shaped curve can relate to sample averages. We care about sample averages because they estimate population averages. We typically can't know everything about a population. So if we have a giant population, it's very difficult to say like this is going to be the population average. But what we can do is we can take random samples, and that allows us to find some sort of sample average that will then help us to predict the population average. So going into more about the central limit theorem, what the central limit theorem says is that if the sample is large and in addition is drawn at random with replacement, then regardless of what the population looked like, so even if the population looks super skewed or the population looks nothing like a bell-shaped curve, what the central limit theorem says is that the probability distribution of the sample averages will look approximately normal. So it will have a bell-shaped curve. So it's roughly normal. So again, just to reiterate, it's saying when you draw a sample at large, random with replacement from the population, then regardless of what the population looks like, that will look like a bell-shaped curve for the sample averages. So it's not saying the sample will look normal, it's saying that the sample averages will look normal. So that's what the central limit theorem says. The distribution of the sample average, you might ask, like, why do we even care what the sample averages distribution looks like? Like, why do we care that it's a bell-shaped curve? You only have one random sample and it only has one average. So when you take the random sample and you get the average of it, that is going to be the sample average for that one sample. But the sample could have come out differently. So let's say that I took a population. Let's say the population is all of the Data 8 class, and I wanted to find the average height of the entire class of Data 8. Maybe it's really difficult to find all of the heights of all of Data 8, so I go through the roster and I find 100 random students, and then I find the heights of them and find the average of that. That would be a sample average. But that's not to say that if I took a different sample, I'd get the exact same average. The population average, so assuming that there's no students entering or dropping Data 8, would remain the same. So the population average of the average height of all of the students in Data 8 should be remaining the same. But depending on how I take my sample, that sample average will come out differently. So there is variability in the sample averages. The sample average could have been different. So let's say that I took 100 students, I could have taken a different set of 100 students, and that would be a different average than the average that I got in the first sample. And that is why we're able to graph some sort of distribution of those sample averages, because when I have a sample average, there's so many different variabilities in how that is created. So you can create a bell-shaped curve. You can't do that with the population average. So the distribution of the sample average, imagine all possible random samples of sample size, and there's a lot of them. So I could take like from the data 8 course, I guess there's around like 2,000 students. I could take a sample of 100, I could take 300, maybe 400. There's so many different sample sizes that you can take from a population. And each of these samples has an average. So we're going to take a little bit of a look at what those sample sizes change or how sample sizes are going to change those sample average distributions. The distribution of the sample average is the distribution of the averages of all of the possible samples. So you are probably not going to be, when you draw the like sample averages distribution, you're not actually going to find every single potential sample that you can take, because there is a lot of different samples that you can take, and we'll go over that in the demo today. But the distribution of the sample average, what it means is that when you take samples, all of the possible samples you can take, if you find the averages of all those possible samples, that is going to be the distribution of the sample average. Okay, any questions before we get into the demo? Yes. So the question is, why with the central limit theorem do we have to draw with replacement? That's a good question. The reason that we draw with replacement for the central limit theorem is because, let's say that we have a sample, right? Let's say that we draw a sample that is like a similar size to the original sample. We do draw with replacement so that it's not going to be the exact same sample as before. Yes. It's kind of like bootstrapping, where you're drawing with replacement, because when you draw a sample, let's say that you're trying to find some sort of sample, but it can't be the exact same sample. We draw with replacement in this case just to get different variations of the sample. If you took lots of different samples with replacement from the population, it would, Noah, in this case, would that also still work if you were to draw without replacement from a giant population for the central limit theorem? Yeah, but in this, yeah. So in this case, we're saying with replacement because it's like you have a set sample, you need to find a sample that's slightly different. But if you had like a giant population that you could take stuff from, then without replacement would also work. Yep. Okay, let's get into the demo then. So I ran this notebook already because the actual code for this notebook does take quite a while to run. So code cells are already run. I'm not going to run it in live time. So this is going to be the first example we're going to go through. So distribution of the sample average. In this case, you'll see that the distribution of, this is the United Airlines like delay times. So this is not a very normal looking curve. You'll see that there's a huge skew to the right. So we say it's a right skew because there's a tail on the right side. This is going to be a right skew. And this is what we're going to represent as like the population. So the population is those United Airlines delay times. Here we'll see that from this population, we can find the population mean and population standard deviation. So let me zoom in a little bit. The population mean is going to be 16.66-ish, and then the population standard deviation is about 39.48 or 39.5. Here I coded something that's called definition of like one sample mean. So you take the sample size, you're going to input some sort of sample size into this function, and it's going to output what the sample mean would be for that sample size. From there, we're going to also code something called 10,000 sample means, which means that I'm going to create 10,000 different samples of that original sample size. So if I put like, let's say 100 here, and then I put 100 here, what it's saying is like, I'm going to get 10,000 samples of a sample of 100. So I'm going to do sample 100 10,000 times is what it's doing. Yes, question? Take a sample from the population of flights. So in this case, this is what we're considering as the population, is the United Airlines delayed flights table. So that's what we're considering as our population. So in this case, we are sampling from that population. Okay, going to the example. So sample means 400. Let's say that I ran that 10,000 samples on a sample size of 400. So I got 10,000 samples of sample size 400. What happens here is I get a population average of 16.65. So you'll see here it's centered at like 16.65, looks pretty normal. This is because I am taking that sample average distribution, and it's going to look like this. So how many possible ways are there that I could have gotten this sample? There are 13,825 rows in the United table, so that's what we're considering as our population. And if I were to get a sample size of 400, how I find how many samples I could have gotten would be the total number of rows in the table to the 400th power. In this case, you'll see that is a really large number that I cannot read, but that is all the number of different ways that you could get a sample size of 400. So just a different perspective of that is a lot of samples. There are many different ways to get a sample size of 400 when you have a lot of data. Just for more examples, let's say that I did a sample means with size 900. So I get 10,000 samples and I do that on a size of 900 instead of a sample size of 100. What's going to happen is I'm going to get a distribution of the sample average that looks like this. So one thing to note is that when I take the samples, if I have a larger sample, so this is size 400 in blue and size 900 in yellow, when I have a larger size sample, the distribution of the sample averages is going to be more narrow and taller. If I have a smaller sample, my distribution of the sample averages will look a lot shorter and flatter. So that is something to take note of. Know that when you have a larger sample, that standard deviation is going to shrink. And we'll go over the law that kind of describes this later in the lecture, but just so that you visually can imagine what it looks like. Because the distribution of the histograms always add up to 100, you'll note that when it shrinks horizontally, it will have to stretch vertically to also make that area 100. Okay. Let's go. So specifying the distribution. Suppose the random sample is really large. We have seen that the distribution of the sample average is roughly bell-shaped. So some important questions remain. Where is the center of that bell curve and how wide is that bell curve? So where is the center means where is that mean of the sample averages, and then how wide is that bell curve is what is the standard deviation of those sample averages. So the center of the distribution. The distribution of the sample average is roughly a bell-shaped curve centered at the population average. So let's go back to the demo. Relationship between this population standard deviation and sample size. You'll see here, when I have a sample size of 100, I get a kind of relatively normal looking curve, but it is slightly still skewed. You'll see here that the population mean is 16.66, like we stated at the beginning of the demo, and the average of the sample means is 16.62. So it's not exactly centered at the population mean, but it is kind of close. You'll also notice that the population standard deviation here is about 39.5, and here it's about 3.9. There's some relationship there. We'll go over that in a little bit. So 39.48 divided by 3.932, you'll get like 10.04-ish. Let's say that I plot the sample means of size 400. So I get a sample size of 400. The population mean is still going to be 16.66, but the sample means average is going to be, again, 16.62. It looks a little bit more normal than this original sample size of 100. So let's see what happens when we increase it to 625. When I have a sample size of 625, the population mean, again, is still 16.66, but the average of the sample means is also 16.66. So you'll see that as we increase our sample sizes, the sample averages are going to be centered closer to that population average. One other thing to take note of is, we'll go over this as like, it's called the square root law. But what you'll see here is that when I had a population of size 625, I had a sample means standard deviation of 1.577. And you'll see that that is when you divide the population standard deviation by that sample averages standard deviation, you get 25. And that is because the sample size is 625 and the square root of 625 is 25. When I had the sample of size 100, I had a standard deviation of like 3.95. The reason is because 10 times that number is going to be the original population standard deviation. So this is going to be called the square root law. We'll get into exactly what it says in a bit. Okay. So the variability of this sample average. Why is it important that we have some variation in the sample average? Along with the center, the spread helps identify exactly which normal curve is the distribution of the sample average. So with the center, we have like, this is what we think it is, but the spread also helps us to identify with a normal curve, like what the sample average is actually going to be. The variability of the sample average helps us to measure how accurate the sample average is as an estimate of the population average. So let's say that I had a really like wide standard deviation. The sample average could be so many different potential things. That's not giving me a lot of information. I can't say with a lot of confidence what I think the sample average is going to be or what I think the population average is going to be. But let's say that I have like a really large sample or like a really lots of different samples, I'm able to say like, oh, with this distribution that I have this amount of confidence that I think the population mean is about this much. So that is why we care so much about finding this distribution. If we want a specified level of accuracy, understanding like the distribution and the variability of the sample average helps us to work out how large our sample has to be. So going back to this demo, you'll see if I only did a sample size of 100, that wasn't a very good sample because it doesn't look super normal. It's not centered at the population mean. So doing this kind of distribution stuff allows us to find what is the sample size that I actually need in order to get the accuracy that I need. Going back to the demo. So the variability of sample means. Sample means, like, let's say that I have different sample sizes. We kind of went over this, but here I have a table of all of these different sample sizes, the standard deviation of this simulated sample means, and then the equation that I would use to find the sample means average. So you'll see here that the standard deviation of the simulated sample means is very slightly different from when I use the equation to find the sample averages, and for the different sample sizes as well. So here I have a scatter of what the standard deviation of the simulated means or sample means looks like and what I would expect it to look like based on an equation. So based on the equation, you'll see that it looks very, very similar. There's like very slight difference in the points for the simulated versus like the empirical, what we got. But this is just showing like there is slight variability in the standard deviation of simulated sample means versus when we do the equation itself. Are there any questions before we move on? Okay. So this is a discussion question. So hopefully you're sitting next to somebody. I would advise you to sit next to someone so you can kind of discuss this question. But this question is, the gold histogram shows the distribution of blank values, each of which is blank. So take a minute to look at this, describe like what you think the answer is going to be. I recommend you read it one more time because when I first looked at this, I think I answered it wrong. So make sure you take a look at it. I'll give you guys a couple minutes, just discuss with the people around you. Okay, I'm going to do a quick poll. So raise your hand if you got a certain number, or a certain letter for the blank, and I'm just going to see what you guys got. So the gold histogram shows the distribution of who put A. Okay, who put B? Who put C? And who put D? Okay, let's see. The gold histogram shows the distribution of, this one's a tricky question. When I first saw it, I put 900. But the answer is not 900. That's really B. It's 10,000. The reason is you'll see the sample size is 900. So when I did the histogram distribution of the sample sizes. It was originally like the gold, it looks like the legend says 900, but that's saying what the sample size is. We're still doing the 10,000 distributions based on that code that we had before. So this is actually 10,000 values, not 900 values. So something a little bit tricky, but when you're doing some sort of code or anything, you want to make sure that you know the difference between the number of samples you're doing and the sample size that you're doing. So this is sample size 900 with 10,000 samples done. The second blank, hopefully nobody put A or B for this, but who put C for the second blank? Okay, and then who put D for the second blank? Okay, this one was a resounding yes for D. This is correct, each of which is an average of the flight delays. So D is correct. We're graphing here those sample averages, and each of the different segments of this is an average of flight delays. Okay, let's move on. The two histograms. So the gold histogram showed the distribution of 10,000 values, each of which is an average of 900 randomly sampled flight delays. What you'll notice is, again, something to take note of, the 900 is a lot narrower and taller, the 400 is a lot wider and flatter. So the standard deviation of that 400 is going to be bigger than the standard deviation of 900. For the blue histogram, which we just saw, that's going to be a distribution of 10,000 different values, each of which is an average of 400 randomly sampled flight delays. So that's sample size 400. When I take those sample averages, I got that blue histogram. Both are roughly bell-shaped, and the larger the sample size, the narrower the bell. So again, the reason for this is if I shrink it horizontally, it still has to be an area of 100%, so I need to increase the height. Okay, variability of the sample average. The distribution of all possible sample averages of a given size is called the distribution of the sample average. So just going over, reiterating so that you guys remember, that sample average distribution is the distribution of all of those possible samples and their averages. We approximate it by an empirical distribution, and by the CLT, it's roughly normal. So CLT, central limit theorem, it's roughly normal because it's a sample average. The center is going to be the population average, and then we're going to go over the square root law in the next slide. So just to kind of quantify what exactly we're saying when we say the sample is larger, so therefore the distribution is going to look a little bit more narrow and tall, we're going to go over the square root law. So what the square root law says is the standard deviation of the sample means equals the population standard deviation divided by the square root of the sample size. If we don't know the population standard deviation, but we're taking samples from like a really large sample, then we're going to estimate that population standard deviation using that entire giant sample standard deviation. So that is the square root law. This is an equation you do want to know because a lot of times people are like, oh, the population standard deviation is going to be the exact same as my sample standard deviation, and that is not the case. Some properties of the square root law. If the sample size increases, the standard deviation decreases. So again, as we saw in the little histogram distribution that we had, when I had a wider distribution, that was size 400, and when I had like a more narrow distribution, that was size 900. So you can see it visually as well, that when you increase the sample size, the distribution for that, the distribution of the sample averages will become more narrow. If the sample size decreases, the standard deviation increases. So again, if I went from size 900 to 400, standard deviation got bigger, the distribution got wider. The standard deviations of the sample will be wider and flatter for smaller samples, narrower and taller for larger samples. And then in order to increase the accuracy of a sample by a factor of size x, you need to increase the sample size by x squared. The reason is, let's say that I wanted it to be like a certain amount more accurate. We're dividing by the square root of the sample size. So in order to make it that amount accurate, I would need to do that number squared for the sample size. Any questions on this before we move on? Yes. Yes, the accuracy, the question was, is the accuracy measured by the standard deviation of the sample means? And yes, in this case, the standard deviation of the sample means is that measure of accuracy that we're getting. Okay, any other questions? Let's move on. Okay, going to the demo. This is just to reinforce exactly what we're discussing in this. So it's not anything new, but let's go over this. So other distributions. In this case, this is going to be a table of San Francisco salaries that were collected in 2019. You'll see here again, this is not a normal looking distribution. This is also slightly right skewed. You'll see there's some little values on the right side of the graph, and that is going to say that's a right skewed graph. And this is like the population that we're going to be sampling from. When I take one sample mean and then again, this 10,000 samples of that sample size, what I get is, again, a roughly normal looking distribution. So just to reiterate, when I find the distribution of sample averages with the CLT, it will tell me that the curve should look roughly normal, centered at that population average. And the population average, you'll see it's centered around that. So CLT doesn't apply to samples looking like a normal distribution, but sample means or sample averages looking like a normal distribution. Okay. Next discussion question. So a city has 500,000 households, and the annual incomes of these households have an average of $65,000 and a standard deviation of $45,000. The distribution of the incomes is pick one of these and explain. So one thing I highly recommend is take a few moments, and if you have any sort of paper or you have like a drawing tool, try to draw out this distribution and see if it looks normal, because that's the best way to figure it out. So take a couple minutes, look at this question, see if you think this is a normal curve or not. Discuss it with the people around you too. This shouldn't be a silent classroom. Okay, hopefully that was enough time to discuss. We're going to go over what you guys got. So raise your hand if you got A. It's roughly normal because the number of households is large. Oh, nobody. Okay. What about B? It's not close to normal. Okay, a few people with that. And then C, maybe close to normal or not, we can't tell given the information. Okay, so a lot of people got like, oh, maybe it's normal, maybe it's not. The answer is going to be B. It's not normal. So the reason that it's not normal, let's go over this. So I know it's kind of a tricky question. So let's say that we had an average of 65,000. What we learned in this class is if we have a normal distribution, 95% of the value should be within 2 standard deviations. So let's say that I had that average of 65,000. If I subtract 45,000 2 times and try to go to the left of 2 standard deviations, I'm going to end up in negative values. While if we're doing annual incomes, we actually can't have negative income. We can't have like negative net worth or like negative other things, but for income, you can't have negative income. So in this case, this is not going to be a normal distribution. It's going to look something like maybe a little bit of a curve here and then like drastically right skew, because we can't go negative in this case. So 95% of those values are not going to sit inside of 2 standard deviations. This is not going to be a bell-shaped curve at all, and therefore this is not going to be a normal distribution. So this is something a little bit tricky. That's why I asked you guys to draw it out. So those of you that did get B, great job. And those of you that got C, you were close. But know that like when you have something and something doesn't look like a bell-shaped curve, it's not going to be a normal distribution because these values actually can't go negative. Okay. Let's go to the next part. Central limit theorem. I'm going to do a quick overview. We're going to have one more review question, and then we're probably going to end a little bit early. So central limit theorem. If the sample is large, to reiterate, oh yes, question. Yes. Mm-hmm. So good question. It's asking, or he's asking why is 95% like not working for those negative values? I guess income's a little bit tricky. You can't have negative income, which is something you would have to know to answer this question. But I guess you could think of it kind of like, let's say that I had an average height of like, let's say 2 feet and I had a standard deviation of 5 feet, right? I can't have negative 3 feet of height. That's not a thing. Like a person can't be negative 3 feet tall. So in that case, like that's kind of what this example is going over. You can't have something go negative when you have a certain value. And that's why this isn't going to be a normal distribution because it's not bell-shaped curve. It could, so yes, that is the case that it could still have like 95% of the values within that area, but because it's not bell-shaped curve, we can't say it's a normal curve because normal curves do have to be bell-shaped. Yeah, good question. Okay, going over to the overview of what central limit theorem says, if the sample is large and drawn at random with replacement, we will end up with, regardless of what the population looks like. So it could be super skewed to the right, it can look super skewed to the left, does not matter what the population looks like. The probability distribution of those sample averages will look approximately normal. It's also going to have a mean centered at the population mean, and the standard deviation square root law says that standard deviation of those sample means, so it says SD here, that's a little misleading. It should be SD of the sample averages is going to be equal to the population standard deviation divided by the square root of the sample size. I think there's one last discussion question. So a population has average 70 and standard deviation of 10. One of the histograms below is the empirical distribution of the averages of 10,000 random samples of size 100 drawn from the population. Which one is it? So try to figure this out. I highly recommend think about what the square root law says and then think about what's the center of this distribution supposed to look like and then decide which one you think it's going to be. So take a few minutes. It's going to take a little bit of calculation. So take some time to do this. But once you figure this out, it'll be like ingrained in your head that this is how I find the standard deviation of the sample averages and how to figure that stuff out. Okay, I heard some good discussion happening from the people that did hear discussing. So who here, just for reference, who here remembers what a point of inflection is? Okay, looks like most of you do, just because I didn't see everyone's hand go up. A point of inflection is where you see something go from concave down to concave up in this case. That is going to be where we say that the one standard deviation mark is for that normal distribution. So let's take a poll. Who got A for this? Okay, who got B? And who got C? Okay, I only saw A's and B's. A would be that you have a standard deviation of 10. That's not right. That's the population standard deviation. The correct answer is going to be B. You'll see that the point of inflection in B is going to be around like 71 and 69. That is because we have one standard deviation looking like a standard deviation of 1. So the reason is if I did the actual standard deviation of the population of 10 divided by the square root of the sample size, in this case, the sample size is 100. If I do 10 divided by 10, I get 1. And that's going to be the standard deviation of the sample average. The standard deviation of the sample average, you'll see, is where the point of inflection is. And you can also see that in B, 95% of those values are approximately within those two standard deviations of 68 to 72. So that's kind of an overview of what central limit theorem is. Hopefully the discussion questions kind of reiterated what you're supposed to look for. But just to reiterate, like, I really want you guys to take this away. If you take anything away from this, is to remember that CLT does not apply to samples. It applies to sample averages. So if it says like, oh, the CLT says my sample should look normal, that's not right. It's only for sample averages in this case that CLT would apply. So if you take one thing away, do remember CLT for sample averages, not for samples. Any last minute questions before we end? Okay. Thanks for attending lecture. If I don't see you guys at Friday lecture, hope you have a wonderful spring break.